Okay, so last time here in chapter 12, we got all mathy on it. Yeah. So we did ice tables last time to solve equilibrium problems. Remember, there's really ultimately we did three different ways that you could solve these problems. Obviously, you could use the quadratic. Um, and by the way, you could always use quadratic if you like it, and you can solve it that way. We also had one that was a perfect square that you could kind of square root both sides. So that does happen occasionally. And lastly, we had the assumption that we can make. And remember that when we make the assumption and we assume x is equal to 0, remember we can only do that in a situation where the k value is small. And that again is the only situation where you could assume that x is equal to 0. Again, the idea behind that is, as we talked about, because the k value is small, that means that the overall change that's going to occur from reactants to products is also going to be small, because we're going to mainly stay on the reactant side. So kind of the reverse reaction kind of mainly happening, but it's going to be negligible, that change. Remember as well, you cannot do that on a large value of k, because it pretty much means the opposite's happening. You're going to have a lot of products, which means you're going to have a lot of change that's going to occur. So again, that is why we did not do the assumption on the previous examples that we did, because our k value was 7 and like 54.3 or something like that. And again, that's too large to do that. Also, a reminder that if you do the assumption, you should always check it. And we check it again using the 5% rule that we talked about. Basically, what you do is you take your x value you solve for, you divide it by the concentration, the kind of initial concentration you're going to subtract that x value from, or in some cases add the x value to, and times it by 100%. If it is 5% there or less, then the assumption is good, and you could use obviously the x value that you got. If you're over 5%, then technically speaking, the assumption is not good, and you would have to go back and solve it. For our purposes here, that would mean you would have to go back and solve it probably through the quadratic formula, as that's probably the only option left at that point. So you could definitely always try the assumption. It will work a lot of times, but there will definitely be a lot of times where it will not work and it will not be a good assumption. So you definitely want to, again, make sure that you do check it. If you don't want to fool with the assumption, again, you could always just go quadratic if you really have the time and want to do that. But it doesn't take too long to run through it and check it. So, it may save you some time along the way. So those will be the three ways that we will solve these type of problems. Remember as well that if you're given sort of initial concentrations of everybody in the problem, that's again another situation where you should calculate Q to verify which way the reaction is going, really the change part of it, as we talked about as well. There is a fourth way to solve these type of problems, which is known as successive approximation, and we will not be doing it that way. But sometimes if you look through books and stuff like that, they solve problems through successive approximation. Successive approximation basically is you have like a number like this, and you know that obviously x needs to be smaller than that number. So you basically pick a number smaller than that, put it in for all the x values except for 1, and then you solve for x. And if you don't get the same number that you put in, then you take the number you got, put it back in, and do it again. And you keep taking the number you get, putting it back in until you get the same number you put in is the same number you get as the answer. And if you don't know how to do it very well, you'll be there all day kind of running through all those options. So we will not do that, but it is also a very common way that people in books and stuff like that will sometimes solve problems. So if you see it, that is a legitimate way of doing that. We, again, will not be using that successive approximation in this class for sure. All right, any questions on any of that there? All right, then we're off to the last part of this chapter, which is Le Chatelier's principle, which I guess is good since that's the lab, I think, today, so that's good. So we're going to talk about Le Chatelier's principle, and the idea of Le Chatelier's principle is this. You basically have a system at equilibrium. So you have a system at equilibrium. And then basically what you do to it is you add a stress to it. And you basically screw up the equilibrium by doing so. Common stresses that we could add to a system has to do with things like concentration. We could either add more or remove. If we are dealing with gases, volume and pressure is another kind of set of stresses that you could do to a system. Um, temperature is another stress that you could add to the system. And finally, something like a catalyst is something that you could add to it. So basically what happens is, as we will talk about here with the Chatelier's principle, is you have, again, a system that is definitely at equilibrium. And again, you do some type of stress to it. What it's ultimately going to do is, as we talked about, these type of reactions, even if you kind of screw them up, will always want to get itself back to equilibrium. So in order to get itself back to equilibrium, there's pretty much three options that could occur. It can either shift to the right, which means you're going to make obviously more products. It may shift to the left, which means you would make more reactants. And there's also some situations that, even though you did something to it, will actually cause no change to occur. So even though you kind of did something to it, there are certain situations where nothing much is going to really sort of happen to that system. And there's a couple of places where that occurs. So again, you're going to do something to it. It's going to screw it up. And then it's going to try to fix itself by shifting to the right, shifting to the left, or again, there may ultimately be kind of no change. Ultimately, what's happening when we shift to the right or shift to the left is we are either increasing the forward reaction to occur, or we're having the reverse reaction to occur in this reversible reaction. So whatever we are doing to the system will basically kick off one of those reactions. It'll either kick off the forward reaction or the reverse reaction. And that's ultimately what's happening in these situations. So let's talk about each of these here. And actually, I think I might just back it up here. So let's talk about the first sort of effect, which is concentration. And again, really, there's two things you could do with concentration. You could add more. And whenever we add more concentration, what always happens is it will shift away from the side we added it to. So a good way to remember that, add away is what will happen. The other thing that we could do is remove concentration. And when we remove concentration, it will cause a shift towards the side we removed it from. So obviously adding is a pretty simple process, right? If I have like a beaker of a system that's at equilibrium, I can just go to the shelf there, grab some type of chemical and dump more of something into the beaker, right? And you could add, for example, if I needed iron, I could go grab some iron 3 nitrate and drop it in there. And I just added some more iron to that equilibrium very simply. To remove something, that's a little bit different, right? So basically, when we have a solution, as you hopefully know, when we have a solution, we pretty much have ions floating around. That's pretty much what's in a solution. That is why it's called aqueous. And we basically have ions floating around. So if I wanted to remove any of these ions that are floating around the solution, do I just reach in with my hand and grab them up? No is the right answer on that. Yes, so you don't want to do that. They frown upon that in the safety video, I think. So we obviously just can't reach in there because the ions are dissolved. They're floating around freely in that solution. So one of the ways that we can remove basically ions or concentration from solution is we could add something to the solution that perhaps will precipitate out some of these negative guys and make a solid. And we know, right, one of the two things that are not included in the equilibrium expression are things that are in the solid state. So by adding something to the beaker that will react with some ions that are floating around and form a precipitate, that is essentially like reaching in there and grabbing out those ions from solution. They're no longer available to just be floating around. It's like removing their concentration and lowering their concentration. So that's one very common way that you could kind of remove something from a solution and lower the concentration by adding some other reagent that will actually make it precipitate, solubility rules and all that good stuff. Another way, you could obviously see that precipitate in most cases being made. Another way that we can very commonly remove something from solution, especially if our solution contains, for example, hydroxide or maybe H pluses, is if I have hydroxide in the solution, which is a base, I could add some acid to it. And that's when H plus and OH minus come together, they make our friend water, right? Water, which is a pure liquid, also not included in the equilibrium. That is a way to remove the hydroxide from the solution. Obviously, you could do the opposite. If you had a more acidic solution with a lot of H plus floating around, you could add some base to it and make some water as well. Odds are you will probably not see that happen because, frankly, it'll just look the same to you because you can't really see water in a sense. You can see it, but you can't see it change like a solid. But that's a very common way if you have an acidic or basic solution, you could kind of remove ions from the solution and lower the concentration. Any questions on that there? Now, if we take a look at concentration here, you can think of it like a seesaw here. This is professionally drawn stick figures. That's advanced stick figures because they have faces, right? Not so advanced that they have hair or anything like that. They just got faces. And if this side over here is, say, our reactant side, and this guy over here is our product side in the reaction, we are at equilibrium at this point. And let's just say somebody decides, hey, I'm going to hop on this side of it. When that occurs, we are going to get this situation. That's going to occur in this particular case. Now, clearly, to fix it, do we need more people on the right or more people on the left? We would need more people on the left, right? So we added to the right is going to shift away from the side we added to. And that's going to return this to a happy for all equilibrium situation, I hope. My stick figure 101 teacher would be so proud. There we go. And we will return back to an equilibrium position at this point. So again, we added products. It's going to shift away to the reactant side. Opposite would be true if you added more reactants. It would shift away from the reactant side towards the products. What's really happening in this case is the availability of the products in this case has now increased, which means that's going to kick off the reverse reaction to occur, which is why it's shifting to the left in this particular case. Now, if we have our same sort of equilibrium here, again, this guy, the reactant, this side, the products. And this guy decides, no thanks, I don't want to be on the right anymore. He gets off. This situation is going to occur. And obviously, in this case, to fix this, we would need to put more people on the right-hand side. So we removed the right-hand side. We kind of made a hole over there, if you want to think about it. And we need to kind of go fill that hole, if you want to think about it that way. And we're going to go towards the side we removed it from. That's going to take us back to equilibrium at this point here. And now everybody is happy. And we obviously learned you should never be on the left-hand side of this thing, right? Because it doesn't seem like the good part of the ride there. Any questions on concentration here? All right. Again, what's really happening here on the right-hand side? We are removing products, right? Which means we now will have more reactants than products. And because we have more reactants than products, that will kick off the forward direction. And that is, again, why it's actually shifting to the right. So really what's happening when you kind of are dealing with the Chatelier's principle, as I mentioned earlier, is you really just kind of want to figure out, are you sort of increasing that forward direction of that reaction? Are you increasing the reverse direction? And that will help you really determine which way it goes. The next sort of stresses that you could do to a system involves when you have gases in an equilibrium system. And when we think about gases, we think about pressure. And when we think about pressure, we think about volume as they are related to each other. When I increase my pressure, what happens to my volume? My volume goes, our good friend Boyle, yeah. Volume goes down, yeah? So small volume, not a lot of space for the gas molecules to fly around in. A lot more collisions happen. Pressure starts to go up. The situation that occurs in that case is when the pressure goes up, the volume goes down. So kind of the change that's occurring is the pressure is starting to rise. So we want to actually kind of bring the pressure back down. Now, because my volume here is smaller, dramatically drawn there, would I need more or less gas molecules in that small volume to bring the pressure back down? Let's start with, will more gas molecules in that small space bring the pressure down? It will not. It'll do the opposite, right? It will bring the pressure up, which is not what we want. So in this situation, because we now have a small volume, we need to go to whichever side of the reaction has the least number of gas molecules. So in this situation, it will shift to the side with the least number of gas molecules. That obviously is reaction dependent. You have to actually look at the reaction or the equation and count up everybody that's got a G next to it, right? It has a gas state, and you can count just the coefficients for everybody that has a G on each side, and that will tell you which way it'll go. Now, opposite of that, if the pressure goes down, the volume will go up in this case. And in that case, what's happening is the pressure is decreasing because now what we have is a situation where we have gas molecules flying around in a bigger area or bigger volume. It's going to take longer for collisions to occur, and that is why we start to see the pressure start to decrease in the situation. So much like the other one, what's happening is the pressure is dropping. So we kind of want to fix it by bringing the pressure back up. So in the case of this, where we have a larger volume, we would actually need more gas molecules in that larger volume to bring the pressure back up. More gas molecules, again, is going to cause more collisions and ultimately cause the pressure to come back up. So in that situation, we would shift to the side with the most gas molecules. And again, that is, once again, reaction dependent as to which side that is. You actually have to look at it to determine it. Personally, when I do this, I relate it to volume, the pressure and the volume relationship. I just think about it in volume, small volume, less gas molecules, big volume, more gas molecules. So this is an easy way to remember that. Any questions on that there? So if we had something like this, So for each of these things here that I'm going to write, will the reaction shift to the left? Will it shift to the right? Or will there be no change? Let's say that we added D, we removed B, we increased the volume, we increased the pressure, we added A, and we removed C. So for each of those, take a moment and decide which way it should shift the equilibrium as a result of these individual stresses. Okay, so let's take a look. So on the first one here, we're going to add more D. So D is on the product side here. And again, when we add, it's going to shift away from the side we added it to. So we add it to the right-hand side. That is going to cause the equilibrium to shift to the left. Once again, what's really happening here is we are now increasing the products. That's going to increase the reverse reaction and cause it to shift, in this case, obviously to the left. We're going to remove B, which B is a reactant. When we remove something, it shifts towards the side we removed it from. So this also should shift to the left. Again, you can think of it as you made a hole on that side, so you kind of want to fill it, and it will go towards that hole. Again, what's really happening in this case is as you remove the reactants, you once again will now have more products than reactants, again kicking off the reverse reaction to occur, and that is again why it's shifting there to the left-hand side. Any questions on that there? Next, we're going to increase the volume, and when we increase the volume, again, the relationship to pressure is going to go down. So again, we have a larger volume, which means we need more gas molecules to fill it. We then have to go to our equation. Each of these are gases. So that is 5 gas molecules there on the left. Each of these guys over here are gases as well. And the coefficients 2 and 1, which would be 3 gas molecules. So in this case, we once again here will shift to the left. In that particular case. Any questions on that there? Obviously, here we are increasing the pressure, which is the opposite of what we just did. That means the volume is going to decrease. So once again, smaller volume means we need less gas molecules in that volume. And in this case, it should shift to the right because it has 3 gas molecules versus 5. We add some A. A is a reactant. When we add, it goes away, so it will shift to the right. Once again, what's happening in that case is by adding more A, that's adding more reactants. By adding more reactants, that will allow the forward direction to occur, and it's going to shift to the right. Lastly, removing C, going to create a hole over there on the right-hand side. I did 3 lefts and 3 rights by just guessing there. That actually worked out. We're going to shift to the right-hand side. Same idea. When we remove our products in this case, we then would have more reactants kicking off the forward direction. Any questions on that there? By the way, with gases is one of the situations where you could get a no change. So for example, let's just say that this reaction's coefficients were, actually I could just do this, pop that in there. Let's just say that this guy was actually a 3 for its coefficient. That would then make this 5 gas molecules on the left, right, and 5 on the right. In this particular case, there is no more or less. This would be a situation where it would be a no change if you did something with the pressure or volume in this situation. So that's one of the situations where you can come across a no change when you're dealing with gases and you got equal numbers of gas molecules on each side of the equation. Any questions on those there? All right, then next stresses is temperature. The good news is temperature works the same as concentration, which means if we increase the temperature, it will shift away. And if we decrease the temperature, it will shift towards it. So the key on this one is to understand where the temperature sort of is in the equation. By the way, when we talk about left-hand side of the shift to the left or shift to the right, we are referring to obviously the equation in the beaker. There is no left-hand side or right-hand side. There's no arrows, right? Everybody's just floating around in the beaker. You know, they're not having the actual equations there as well. So what determines sort of where the temperature is what type of reaction you are dealing with. Is it exothermic, which means heat and energy is released? And I would say probably almost 100% of the time, how that will be displayed to you is through what is known as delta H, which is the change in enthalpy. Change in enthalpy is chapter 6 in the book, I think. And it's basically the heat of a reaction. And when delta H is there and it represents a exothermic process, the delta H value will always be negative. So if you see a negative value for delta H, that represents a exothermic reaction. And usually, like I said before, you're usually just given the equation, and at the end, it gives you like the delta H value. In this application, the number is not really important. It's actually the sign that's most important here. Now, what does that mean? When we think about it in context of Le Chatelier's principle, we think of energy being released, which means we think of energy as a product. Not really correct in all aspects, but for Le Chatelier's principle, it works. We think of energy as a product there, heat or energy as a product. That means if you have an exothermic reaction and you increase the temperature, it will shift to the left. And if you have an endothermic reaction and you decrease the temperature, it'll be like removing products and it will shift to the right. So again, it works the same way as concentration. The other option is an endothermic reaction. Endothermic heat and energy is absorbed. And usually the delta H for an endothermic reaction will be a positive number. So if you see a positive number for the delta H value, it is going to be an endothermic reaction. Opposite of exothermic, since endothermic means it's being absorbed, we think of heat and energy as being a reactant. So we think of it as being on the reactant side here of the equation. So if you have an endothermic reaction, if you increase the temperature, it will shift to the right. If you decrease the temperature, put everybody on ice, it will go back the other way to the left-hand side there. Any questions on that? So really, you have to kind of determine what type of reaction you're dealing with. And like I said, this is probably how you would do that. That's probably most likely how it would be presented to you. Or they could write it directly into the equation. Not very much happens with that usually. In our class, we usually just get kind of the delta H values because oddly, the book thinks you've already done chapter 6, which would make sense. It's around 12. So they think you've already seen delta H, so they usually will display it as delta H. Any questions on temperature there? The last sort of stress that you can do is, we got rid of that there, is add a catalyst. And if you're not sure what a catalyst is, let me tell you what it is not. It is not a reactant. It is not a product. and it does not get used up in the reaction. It is usually there to facilitate a reaction occurring faster by finding a more efficient alternative pathway for that reaction to occur. Typically, catalysts are written up there on the arrow usually. Maybe it's a metal like platinum. Maybe it's an acid as a catalyst, but they sometimes will write it up there on the arrow. The good news is a catalyst will pretty much be the other way that you could get a no change situation. So you'll just get there quicker. It won't really cause any type of shift in equilibrium, and it will not cause any change to occur. Other ways, besides obviously equal numbers of gas molecules that we talked about for no change, if you add a noble gas, for example, since they're chemically inert, they typically will not cause any type of change to the equilibrium as well. Any questions on any of those there? All right, so let's just kind of go through those. Obviously, concentration, as we talked about, again, will shift away. For added, it will shift towards wherever you remove it. Temperature, right, as we also talked about, is the only thing that will actually change the numerical value of the equilibrium constant. But again, we treat it as either a reactant or a product, depending if it's an exothermic or endothermic reaction. Pressure, again, an inert gas does not affect the equilibrium position. So again, if you added some type of noble gas, not going to have an issue. Again, with the pressure, it is usually linked to volume. And again, volume is a good way to think about it. Small volume, less gas molecules. Larger volume, more gas molecules is what you need. All right. So, hey, why don't you try this? So for this reaction here, we'll go with the delta H is negative, which might not be true. Will it shift to the left? Will it shift to the right? Or will there be no change for this particular one if you do each of those things? So take a few moments there and decide which way we're shifting. Okay, let's take a look. So in this case here, we're going to add some H2. So H2 is a reactant. So when we add, it shifts away. So we would expect it to go to the right in this case. Again, we're increasing our reactant. It's going to increase that forward direction of the reaction. We'll go with removing NH3. NH3 is a product that's going to create like a hole on that side. So we always go towards the side we removed it from, which means this will also go to the right. Once again, by removing those products, we're actually increasing the reactants and the forward direction is going to kick off. Adding N2, a reactant, when we add it, will shift away. So we will shift to the right in this case, as the forward direction of the reaction will predominate. We're going to lower the temperature. So temperature, again, is related to the type of reaction that we're dealing with. And my made up delta H here of it just being negative tells us that it is exothermic. And because it's exothermic, it's going to release energy. And because it releases energy, we think of heat and energy as a product in this case. So what we're doing when we lower the temperature is actually removing some products, and that's going to cause the forward direction there to occur and it to shift towards that side, and it will go to the right. Yes, sir. Uh, it does depend. It depends on some factors. Um, it depends on the bonds you're making and breaking. So there's a whole kind of accounting of what you're putting together or what you're breaking. So when you do delta H of the reaction based on bond enthalpy, which is what you're talking about, you have to add up. You might have done that when you did the bonding chapter, perhaps. You have to add up all the bonds you break, and it depends if they're single bond, double bond, or triple bond as to how much energy cost that is, and in terms of what you're making as well. How much energy cost that you got on the other side. So it can depend on sort of the reaction and what's being made and what's being broken in terms of the energy cost in terms of bonds being made and broken. Other questions? Usually these delta H values are calculated, and again, you may be familiar with or not, but when we get to chapter 6, we'll talk about it. But they're usually calculated by what's known as the delta H of formation, and it's an enthalpy value based on sort of the formation of these elements and so forth. And it's kind of the difference. It's what's known as the state function. So it's the difference between sort of what you make on your product side, which is your final state, and where you started with, which is your initial state or the reactant side. And that's how you calculate delta H, by taking the difference of the delta H's of the products minus the delta H of the reactants. Yeah, so in this particular case, by lowering that pressure, I'm sorry, by lowering the heat or energy in this case, you're actually removing the product. So that change is going to be a lot more than obviously the everybody will slow down. You'll have less collisions, so you will see the pressure decrease, but it's that decrease in um, the temperature that's going to be the ultimate thing that's going to kind of cause it to shift that way, because in this case we're sort of treating the energy as our heat as like a product or a reactant, and it'll have sort of a greater effect on the shifting of the equilibrium. Yeah. Yeah, so in this reaction, and again, if you actually do the calculation, it may be positive or negative. I think I might have just made up the negative just for the aspect of the Chatelier principle part of it. But when you see this number, that calculation has already been done of the energy difference that's going to happen as it goes from reactants to products, the difference in energy of the products versus the difference in energy of the reactants. And that's essentially how you calculate the delta H value for a reaction, is you take the delta H of all your products and you subtract it from the delta H of all your reactants. And that's ultimately, in terms of the number, going to give you a positive or negative, which means in this made up example of what I just said, it was negative. It means overall this reaction is releasing energy as a result of those products being made versus what you are kind of breaking apart on the reactant side. So that sort of decision of sort of where the energy and what's happening with the energy is sort of decided before you do something to it in terms of changing the temperature and stuff like that. Yeah. Other questions? Okay. We're increasing the volume. So when we increase the volume, the pressure will decrease. And when we increase the volume, again, that's a good thing to think about. Larger volume means we need to go to whichever side has more gas molecules. And in this case, these are all gas molecules on the left-hand side, and that's a grand total of 4 gas molecules by just adding the coefficients. On the right-hand side, we have only 2 gas molecules. So in this case, we would shift to the left to try to bring the pressure back up as a result of that. If we increase the pressure, again, our volume here is going to decrease. That's going to give us a smaller volume, which in this case would cause it to shift to the right there, as that has, again, 2 gas molecules versus 4 on the other side. Any questions on those there? All right, let's see. All right, let's just do this one, and we'll go endothermic on this reaction, which means the delta H will be positive. And again, we're wanting to know, will go to the left, will go to the right, or will there be no change? Let's see. Let us decrease the pressure. Let us add O2. Let us remove N2. Let us increase the temperature. Let us add a catalyst. And lastly, let's see, let us. Okay, so looking at this here, we're going to first decrease the pressure, which means our volume will increase. Put a V there. And again, in the larger volume, we want to go to whichever side has the most gas molecules. In this case, these are both gas molecules, which gives you 2 gas molecules there, and that is 2 gas molecules there. That is a push in that case. That is a no change in that particular case. Again, we remove, put some arrows in there, that'd be good. Remove some N2. That is a reactant. So when we remove it, will go towards the side we removed it from, which means it will go to the left there in that case. Once again, you'll have more products and reactants kicking off the reverse reaction. If we add a catalyst, that also will create no change. If we add O2, that's a reactant, which will shift away from it, again, increasing the reactants in this case, causing the forward direction of the reaction to occur. We're going to increase the temperature, endothermic, and again, I would know it's endothermic because it has a positive delta H value. That would mean that it absorbs energy, and we think of heat and energy as being a reactant. And now we treat it just like any other sort of reactant or product. And in this case, we're going to increase it, which means we're going to shift away from that side. Again, you can think of it like adding more reactants, going to cause the forward direction basically to occur. Here we're going to add some NO, which is a product, going to shift away and should go to the left. Any questions on Le Chatelier's principle there? Well, one chapter down for the semester. There we go. So we are going to quiz it up, I think, next to chapter 13. This is about acids and bases. So just a reminder, acids in terms of nomenclature, so we remember how to name acids. Acids, the cation for all acids is H plus. And when we name acids, it does revolve around whether or not there is oxygen involved. And when we do not have oxygen, so if your answer is no oxygen in your acid starts with hydro something ic acid. The missing part is the anion to our acid. So HCl, acids typically have the aqueous symbol next to them to indicate that it's an acid, and that is hydrochloric acid in that case. If it was in the acid, I was going to write what I was going to say. If it's in the gas phase, it would be hydrogen chloride gas. So we throw a little hydrogen chloride gas in some water, get a little hydrochloric acid, HBr, hydrobromic acid, right? If your acid does have oxygen, then it'll probably contain everybody's favorite thing, which is those polyatomic ions, dare I say. And as you, I'm sure, remember, the polyatomic ions end in one of two ways usually. They either end in ate or ite is typically the two sort of endings for most polyatomic ions. If your polyatomic ion in your acid with oxygen, which are sometimes referred to as oxyacids because they contain oxygen, if it ends with ate, your polyatomic ion, then it is something ic acid like HNO3. NO3 is nitrate. This is nitric acid, right? H2SO4. SO4 is sulfate. That will be sulfuric acid, right? We have two hydrogens because sulfate is -2, right? To balance it out to 0, each of the hydrogens +1. So that is why we have it, also known as a diprotic acid, right? Like your titrations, maybe you had diprotic, monoprotic, or triprotic acid. If your polyatomic ion ends in ite, your acid will be something OUS acid. So if you had HNO2, NO2 is nitrite, ITE. That would be nitrous acid. H2SO3, SO3 is SO3 2 minus, which is sulfite. That would be sulfurous acid, right? Bases are oftentimes named like normal. A lot of the strong bases come from group 1 and 2 on the periodic table. They have hydroxide in them, like sodium hydroxide, potassium hydroxide, calcium hydroxide, and so forth. Any questions on acid nomenclature? Hopefully review, I hope. All right, so let's talk a little about acids and bases. Acids have a sour taste. Vinegar is the basic component of vinegar is acetic acid, which is a weak acid. Citric fruit contains citric acid. They react with certain metals to produce hydrogen gas in some of those double displacement reactions you might remember. Like you take a little zinc and a little hydrochloric acid, and it does a little knockout move there, and you end up with some zinc chloride. And when hydrogen gets kicked out by itself, it becomes hydrogen gas. I'll balance it like I'm a chemistry person here. There we go. A little 2 in that case. So when hydrogen gets kicked out, it becomes hydrogen gas, and you obviously see bubbles. Acids also react with carbonates and bicarbonates to produce carbon dioxide. If you take an acid and maybe some sodium carbonate, it does a double displacement reaction where they switch partners, and you end up with NaCl and H2CO3. Let's talk a little about acids and bases a little further. Sort of a basic definition of acids and bases was done by Arrhenius. He said that an acid is a substance that's able to produce H plus or hydrogen ions in solution. One of the first things that you should be aware of when we're talking about acids and bases, especially with acids, is H plus, which is the hydrogen ion, represents an acid. And H3O plus, which is known as the hydronium ion, is for all intents purposes the same thing. They are interchangeable. You could use them interchangeable in equations, formulas, and stuff like that. I will say nowadays books use H3O plus a lot. I personally use H plus a lot because I don't know why, but I just do. But so wherever I put an H plus, you could kind of put an H3O plus, and it's basically the same thing. Now, why would you get, for example, say H plus versus H3O plus? It really has to do with how you write your reaction or your equation. Now, when we take something like hydrochloric acid, which is this, it's a strong acid, and that makes it a strong electrolyte. And if you remember what strong electrolytes are, there are things that will 100% break apart into ions in solution, conduct electricity very well. And you could absolutely show hydrochloric acid when it goes into solution like water and as a reaction between hydrochloric acid and water. And you basically will get a double displacement reaction sort of occurring here. And you will produce, as this guy kind of sends its, not really double displacement reaction in this case, you'll send your H plus over, and that is what's going to produce the H3O plus. So because they included water in that dissociation of the strong acid into its ions, you will produce H3O plus and chloride ions. You could absolutely sort of write this reaction in a more cleaner way, if you will, by just saying HCl, which is a strong acid, and an arrow breaks apart into H plus and Cl minus. Both of these equations are correct. Both of these equations are equivalent to each other. I chose not to include water in my dissociation here because it's basically just falling apart in water. And I get H plus versus the H3O plus when you do include water. So you could write them either way. I would say your book will probably include the water and the H3O plus when you look at those equations. But H plus, H3O plus, pretty much same deal. It basically represents the acid part of the solution. Now, what makes something an acid is its ability to produce, and this is important, it's able to produce free H plus or H3O plus in solution, not attached to anything else, just free floating around H plus. The more H plus ions you have in solution, or the more hydronium ions, H3O plus you have in solution, the more acidic that solution is going to be because they are freely floating around. As we'll talk about, that will affect the pH of that solution based on how much H plus is floating around in there. Arrhenius defined a base as something that has the ability to produce hydroxide in solution, OH minus. It's kind of the same idea. For something to be a pretty good base or just a base in general, it needs to produce free-floating hydroxide ions in solution. Now, what we have here is ammonia. Ammonia actually is a weak base. It's a very popular weak base. When it reacts with water, it will actually accept an H plus from water. And as a result of that, water will now become hydroxide. And now it has basically produced hydroxide. And that is what makes ammonia a base. It is a weak base because it's a weak electrolyte. You might remember weak electrolytes have arrows that head in both directions, like we see here. Definitely an indication that this is a weak base and a weak electrolyte. Now, when you have a strong base, like you get if you go to the periodic table and you go like lithium and you go sodium, you go potassium, hang a right-hand turn there to calcium, a little strontium, maybe some barium. You hook any of those guys up with some hydroxide, you probably just made a strong base. Base is sometimes, basic solution is sometimes referred to as being alkaline, right? And if you think about the names of those two groups, that is the alkali metals, right? And the alkaline earth metals. And those are the bases of some strong bases. Now, different than ammonia, sodium hydroxide is a strong base because frankly, it's carrying hydroxide with it. So all it has to do is go for a swim and it's going to completely break apart into ions because it's a strong electrolyte and it will produce a lot of free OH minus in that solution. And that is why we also see a one-way street there, arrow, because it's going to completely break apart into hydroxide as opposed to this guy that's going to kind of mainly stay together and produce a little bit more of hydroxide. Again, it's a stronger base because, like I said, it pretty much has hydroxide on it. Ammonia's got to go find some water, do a little reaction, right, and produce some hydroxide. So it's not going to produce as much as you would get by just dumping some sodium hydroxide into a beaker. Now, a more general definition of an acid and a base is the one that is given to us by Bronsted Lowry. And Arrhenius' definition was a good definition, but he did a lot of work with bases that had hydroxide in it. And this more general definition is the Bronsted Lowry definition. Bronsted Lowry definition is an acid is a proton donor. Hence the third way that we talk about an acid. H plus is also referred to as a proton in acid-base chemistry. And that is because, as you might know, right, hydrogen has one proton and one electron, no neutrons, right? And you become positively charged by losing electrons, which leaves it just a proton at that point. So it's referred to as a proton in this case as well, very commonly here in the acid base chapter, and definitely when you're talking about Bronsted Lowry definition. A proton donor is something that will give away an H plus. Bronsted Lowry base is somebody that will accept an H plus. And in this particular case, our ammonia is our base, and believe it or not, water is our acid. Water is going to donate an H plus over to the NH3, and that's going to make the NH3 the base that's going to accept that. when it accepts the H plus or when somebody loses an H plus, people oftentimes screw up the charges. So just a reminder that it is not just a hydrogen by itself. It has a +1 charge, which means if you gain the positive charge, you will become one more positive than you started with. If you lose the H plus, you just lost one positive charge, so you'll become one more negative than where you started with. So our NH3 is neutral. When it gains the H plus, it becomes NH4 plus, which, as we know from our polyatomic ion deal, that is the ammonium ion. Yes, not to be confused with the guy on the left there, which is ammonia, right? And when H2O, which is neutral, loses the hydrogen, it has one less hydrogen, which leaves it an O and an H and becomes one more negative. So from neutral becoming one more negative makes OH minus on this side. A consequence of the Bronsted Lowry definition is this: it actually will create partners on opposite sides of the arrow. So our base over here is related to this guy on the right-hand side. And on the right-hand side, this would be known as the conjugate acid. So the base on the left-hand side is related to what is known as conjugate acid on the right-hand side. And our acid on the left-hand side is related to this guy over here on the right-hand side. And that is what is known as the conjugate base. So there is always these partners and relationships that occur in the Bronsted Lowry definition. And the absolute only difference that there can be between, say, a base and its conjugate acid, or that acid and its conjugate base, is this guy right there. The only difference can be one H plus difference, is the only difference between those things that are considered pairs. If you have anything that is more than one H plus difference or more element difference, those things are not related to each other in terms of Bronsted Lowry acid base conjugate base pairs. And as we go from the base on the left to the conjugate acid on the right, it gains the H plus, so it has one more H plus than it started with. And the acid, as it goes to the conjugate base, because it got rid of its H plus, will have one less H plus than it started with. Any questions on that there? Now, if we take a look at an earlier reaction, which is actually this one here, just get rid of everything on this page. We take a look at that dissociation of HCl and water, and we take a look at this equation. What's happening again in this situation is the HCl is our acid. Water is actually acting as the base in this case, and it's the acid in this one sending the H plus over. Once again, when it does so, when that HCl loses its H plus, it will create its conjugate partner on this side, which is the conjugate base, which is the Cl minus. When water, which is in this case our base, gains the H plus, it will create H3O plus, which is that hydronium ion, and that will be our conjugate acid. By the way, regular old acid and bases are always found on the left-hand side of the arrow. On the reactant side, your conjugate partners are always found on the product side. So anything that's conjugate base or conjugate acids on the product side, regular old acid and bases are on the reactant side. Now you might notice in this particular situation, again, the only difference is one H plus as you go from one side to next. But you might notice that when we look at this reaction we just looked at here, water is actually acting as a base, but yet when we look at this reaction, water is acting as an acid. There are certain substances that can act either as an acid or base. Those things are what are known as being amphoteric. An amphoteric substance can act as an acid or a base. Water is typically something that can do that. Also, things that typically have a hydrogen and a negative charge can typically do that, like HS minus. It could act as an acid or a base because it has a hydrogen to give. And because it has that negative charge, it actually has a hydrogen available to sort of accept, or room for the hydrogen to come in. So typically things with kind of like a hydrogen, some type of negative charge, typically kind of go either way. We'll talk about it in this chapter and future chapters as how you know which way it will actually maybe behave in terms of an acid or a base. But those things can typically go both ways. But water, very commonly an amphoteric substance that in certain situations will act as an acid, and in other situations will act as a base. Any questions on that there? All right, good place to lay it up there.